thanks everybody for coming tonight. I'm excited to see a lot of people. So this talk is sort of looking back a little bit. I think microservices is something that people are talking a lot about these days. But in a way, the architecture is not unlike what we did at Google a little more than 15 years ago. And I want to talk a bit about like the choices that were made at the time and why Google chose to adopt that architecture. I also want to talk about maybe where it's not the right choice for other people and maybe where it failed in a big way. I think it's really important to talk about failures and what we can learn from them. So my name is Daniel Spoonhauer. Everybody calls me Spoons. I'm the CTO and co-founder at Lightstep. And I would just, as a general point of order, if people have questions, just like wave, yell them out. I'd love to have discussion. If there's anybody else who's at Google or was at Google that remembers these things better than I do, please shout it out and correct me where I get it wrong. Cool. So let's just kind of set the stage a little bit. So what was happening? What led to these choices that were made? What was the point? So what these guys were betting on, Larry and Sergey, was that they were going to build this box, and you were going to install that box in your data center, and that box was going to index and allow you to search a bunch of documents that you had there. It turns out that that is not as valuable as a near monopoly on all digital advertising. And so in the end, being able to scale not just to like what a single organization might have in terms of their documents, but what the whole web had to offer was really important. So my part in this, I joined actually after a lot of this had happened, but I worked with a lot of people. I think I can relate a bunch of the stuff that happened. And when I was there as part of technical infrastructure, it was actually kind of an interesting time in that it was sort of a mature market in a way, and I'll talk a bit more about that. So we had a lot of different kinds of users, at least different as far as Google engineers go, so maybe not that different, but different in some ways that I think are important. So great. So the thing that motivated a lot of this early work at Google is those Sunboxes, that hardware was kind of expensive, and maybe by kind of, I should say, really expensive. So, someone asked, maybe we shouldn't buy really reliable hardware, and I think that question and that choice actually led to a lot of what Google did, and Google got really good. I think the reason, in a sense, that Google succeeded in a lot of ways is they got really good at building fast, reliable systems on top of really cheap hardware. So I mean, good in the sense that they got really cost efficient. There's a story that I think is true that Urs Husel, who later went on to like run all of technical infrastructure, at the time he was just doing sort of whatever needed to be done. That the story goes that he actually dumpster dived at a RAM manufacturer and like found a bunch of broken RAM to bring back, and they wrote a bunch of code to figure out like where the bad sectors in the RAM were so that they could use the good ones. But that sort of, I think, epitomizes the kind of the mentality here, which is like to be able to build sort of whatever you had at hand, and to build sort of from this sort of super scrappy kind of mentality. So they solved this problem through dumpster diving and some other things, but man, those Linux boxes are really unreliable. So, I mean, that's what happens when you kind of duct tape these things together. And this motivated a lot of design decisions that were made in terms of how do you build on top of hardware that kind of sucks. Also, an operating system that at the time also kind of sucked. I mean, no disrespect to the hardware people at Google, they were trying to like really build right on the edge of failure. And Linux has come a long way, but at the time Solaris was a lot more robust in many ways. So. Yeah, so great, we're going to build some distributed systems on some unreliable hardware. Cool, I guess we're not going to go. This is sort of what GitHub looked like in 2001. So you could go check out GNU, or you could go Apache Foundation. And I don't mean this in like a pejorative sense, like these are great organizations, like they're building some great software, but these are not the tools that you would want to build a sort of planet scale system for crawling, indexing, searching the web. Google kind of had this not invented here mentality in a lot of ways. Back at the time, it's sort of by necessity, right? Like the things that they needed weren't invented anywhere else. And so they had to build them all the way, from the hardware, this version of Red Hat 7.1 that at least when I left 5 years ago, they were still maintaining a patch of. And this, I think, I don't know, if Google were founded now, and that made sense from like, an advertising point of view or whatever, I'm not sure that they would do this right. I mean, they would just do what we do, right? They'd go experiment with some hosted services. They'd use AWS, and they'd kind of go from there, and maybe adopt some open source technology as they needed to. But at the time, like these things weren't really options at all. So if you were an engineer back in the day, first of all, you have to build this thing that's going to scale horizontally. There's not a box big enough. I mean, this was also sort of the time of Alta Vista. I don't know if anyone remembers the giant machine that Alta Vista built to try to page all of the web into RAM. That wasn't the approach that Google was going to take. Your software had to be fault tolerant because it was going to run on this kind of crappy hardware. And you had to do it yourself because these technologies didn't exist at the time. And in some ways, these are pretty different than I think what we do today. Sure, we have to scale horizontally, but there's a lot of things that help us do that. There's a lot of open source software and other systems that we can use to do that. Yeah, sure, AWS instances go away from time to time, but not the failure rate that Google internally maintains to kind of keep costs down. And certainly don't do it yourself. That's not the approach that folks take today. So a lot of things have changed in some way. The other thing sort of joining at the time, and even later at Google, you were joining this organization of really intellectually rigorous people. Google benefited a lot from the sort of implosion of a bunch of different research labs. At the time, Deck Labs, a lot of really great people Sanjay and Jeff and Sharon Pearl, who actually laid the seed for Dapper, which then became a bunch of stuff that I'm involved in. But folks that were really high quality distributed systems researchers, and in a sense, when you have that hammer, everything starts to look like a nail. So that sort of led to a bit of what they did. Google also had this super aspirational, ambitious attitude that they were going to do this amazingly large thing, and in a lot of ways we're quite successful to that, and maybe partly because there was a little bit of intellectual vanity, but I mean, like I said, they were pretty successful. So this is sort of the environment that we were in at the time. So what happened? There was this sort of explosion of these infrastructure projects. So I think a lot of people are probably familiar with some of these. Borg, maybe a little bit. This is sort of the thing that led to Kubernetes in a lot of ways. Mustang sort of does the brunt work of a lot of what web search does. But just to take GFS, Google file system is not really a file system in a traditional sense. It's not NFS, but better or something. It's just a different thing, right? One of my co-founders, Ben, as an early project, it's sort of on the side, he was oh, I know, I'm going to write a shell expansion tool for GFS. And someone was no, GFS is not for humans. That's not the thing to do. GFS is built as a storage system for these highly distributed computations, and it supports things multiple concurrent appenders to a single file, which is really important in a distributed system, but not as a human. At the time the MapReduce paper came out, I was actually in a functional programming language group doing some research, and all these functional programmers were MapReduce, those things have been around for decades. There's nothing new here, right? And from a purely mathematical sense, no, there wasn't new. The thing about MapReduce that was kind of amazing is the scale that it could operate at in terms of the data sets, in terms of the resilience to failure. So I think it needs to look at the scale and look at the way that the projects, what they decided to do and not do. And you can say the corners that they cut, but SmartAss, which was the smart ad selection system, that from a pure machine learning point of view was a little bit shady at times. But when they deployed it, I think they served 25% less ads, fewer ads, and made 30% more money or something like that. So from the point of view of getting something out there, getting it used by people and making an impact, these all were extremely focused on that and extremely focused on the scale. So what happened? What about everyone else that wasn't working on one of those projects? We all sort of looked up to those projects. We all wished we could work on the next version of GFS or something like that. And so we all kind of took this mindset to the other things that we were working on. So, we of course wanted to look for these things. How can we build these things at scale? And we looked to sort of how those. I think this might be a little bit better for you. Cool. Thank you. Oh yes, much louder. Cool. Tell me if I get too loud. But now I can hear myself too, so that's kind of fun. So how were these things built? One thing that was done really well is that each of them factored out a lot of these core services, whether it be RPC, load balancing, service discovery, later things like tracing and authentication. And those were all factored in a way that could be reused easily. So as a new engineer sort of joining Google, like, I have this like crazy aspirations of building this like giant service, but cool, I've also got the tools to do that. That's going to be fun. Then we didn't exactly do like continuous integration and delivery, but things were rolled out weekly or something like that. At least that was sort of what we're all aspiring to. And so in a lot of ways, this, I think, if you sort of look at it and squint a bit, like, this is the kind of thing that we aspire to through things like microservices. So there are some parts that are similar. I wanted to mention sort of on this like factored out infrastructure in a way, at least when I left, if you just wanted to build like the Hello World binary at Google, like it did nothing but print out Hello World, but you linked in all of the libraries that got you this sort of insane user space distributed operating system, that binary is 150 megabytes. And so there's a lot of cool stuff in there. It was sort of a pain as one of those teams, because if you wanted to update your software, you need a lot of binaries to be recompiled. So, after a week, probably, maybe about half the fleet got your change. So like, we're going to make a change to the tracing library or something like that. And after 2 weeks, maybe about 90% of the binaries were redeployed. But, a year in, you've hit about 98% or something like that. But there's this last like few percent that those binaries are just going to be there for years, and you just have to deal with the fact. So I think there's some things we can definitely learn here in terms of what folks are doing now with things like service meshes to decouple the deployment strategies for what might be sort of like user space OS, and decouple that from the deployment of the service and the application itself. Okay, cool. So that's sort of like what was there. What can we learn from that? So part one, know why you're adopting microservices. I think this is really important. At Lightstep, we hosted this sort of set of talks that we called Dreams and Nightmares of Microservices, and we had invited a couple people to come talk about their own sort of dreams and nightmares. And VJ Gill, who's runs engineering at Databricks now, talked in his talk about the one good reason to adopt microservices. And in his words, is that is so that you can ship your org chart. That is the reason that you should adopt microservices. Nothing to do with performance, nothing to do with scalability. It's about making teams of engineers be able to work independently. The idea is that you can't get more than maybe 10, maybe 12 folks to work together collaboratively on a single piece of software. And there's a bunch of research that VJ kind of talks about that shows why that's probably true. And it's just like a human brain communication thing. Like, you just can't keep the state of those other people, and you can't make the sort of working set small enough to be effective. And so if you want to build something that's going to take more than 10 engineers, you're going to have to figure out how to divide up your software in a way that you can get those teams to work independently. So that's kind of, at least, I think I buy a lot of this. Like, there's, I think, a confusion between sort of, I want to run a process and I want that process to scale in like a very low-level kind of implementation point of view, and a distinction between that and a service, which I think about having an SLA, and it might be that that's implemented as a process, but it might be that there's a thick client library, or it integrates with my service mesh or something like that. So, I mean, the thing I want to call out, though, this is pretty different than the reason that Google did it, right? Google was doing it because they had this fleet of unreliable hardware. They needed to scale out things really quickly, it wasn't really about trying to like support this big organization. Like, the organization was pretty small at the time, and they were trying to really support web search and web ads and building this sort of planet scale thing, right? So, obviously, what's best for search and ads is best for everyone else. Not true. So there's this conjecture I think I've heard attributed to Jeff Dean. And the idea is that you can't build a system to handle more than 3 orders of magnitude of scale. Or if you try, it's just going to fall apart in some way. So Google does, I think the published number now, or was, I have no idea, but it's something like 2 billion requests per second. And so if you want to build, say, I don't know, a tracing system to handle 2 billion requests per second, you're just going to have to cut out a lot of stuff. Like, you're going to have to cut out features, you're going to have to cut out usability. It's going to be probably hard to use, but that's fine because you're at the scale. But if you're only handling, I don't know, 1 million requests a second or something like that, there's actually a lot more that you can do, and those are really different things from sort of like a requirements point of view, like almost categorically different. I worked on a bunch of different configuration tools at Google, and this is sort of a perennial problem for me. So maybe if any of you are in SaaS or B2B businesses, you have a similar sort of pain, but Working at Google, I had a couple of really big customers, namely search and ads. And search and ads basically print money. So they can buy anything that they want. They can scale, and like they had whole teams of people that were sort of responsible for just like integrating with my little configuration system. At the same time, like for someone like search or ads, like 1% efficiency is a huge, like a 1% efficiency loss is a huge thing for them, or again, also a huge thing for them. So they're like operating on these really like tight margins in a way. And if you look at the other like 1,000 teams at Google, they're just not the same, right? Like when I was working on these projects, we were trying to figure out like who our customers were, and the sort of poster child for everyone else for a long time was Google Calendar. And I think at the time, Google Calendar was like 10 people that was like building, maintaining, and like operating that. And like Google Calendar's not small. Like, I don't know how many people use it, 100 million, like a couple 100 million. Like a lot of people use Google Calendar, but it was this tiny thing. And to think that that team like needed the same things, like they weren't printing money. They didn't have infinite resources. They had, relatively speaking to infinite, zero resources. So it turns out, yeah, that like actually, what's best for web search and ads was like best for all of the planet scale applications that we have. But that turns out not to be a lot of organizations, and I think probably not a lot of organizations that are out there in the real world as well. I don't know if anyone was at Google at the time, and this rings a bell for anyone. At least a couple people maybe, yeah. So there's some website you can like upload a script to it, and it like animates it with like cartoon characters that kind of like play a video of your little thing. Some engineer at Google wrote this script where the premise was there was someone who just wanted to serve 5 terabytes. And 5 terabytes being like more than would fit on a particular machine, but like not that much data, right? It should be pretty easy compared to like the other stuff that was happening at Google at the time. And the video kind of went through this like series of obstacles that were placed in front of this one engineer. And that was sort of this like dialogue between these two engineers, and one constantly asking for help about like, I just need resources to do this thing. I just need some compute. Okay, well, here's the form you need to fill out. Like, okay, well, I need to run in multiple regions to, be highly available. Okay, I guess here's the other thing I have to. I have to set up my own like monitoring infrastructure in order to monitor my service. Okay, I guess I'll do that too. And like over and over, like I have to get, sign off from production readiness. And like this, I think my boss like forwarded me an email that his boss had like forwarded me like, hey, did you see this thing? I was like, yes. We all saw this thing. Like everyone felt this pain in a lot of ways. I mean, everyone besides web search and ads. And like this was sort of like the calling for like figuring out like how do we serve these smaller teams. So I guess this is kind of the lesson, like think about the scale that you're operating at, because what was right for web search is maybe not what everyone else needs, at least in some cases. So, okay, lesson 2. I have to channel Ben a little bit. Ben gets really mad about the word serverless. Like it's good. It tells you it's great from like a marketing point of view, and it gets you like asking more questions about what it is. From like a implementation, like discussing architecture, it doesn't tell you anything, right? It's kind of like NoSQL. Like, well, it's not SQL. It's not servers. There's a lot of other things that are serverless too. I think Ben likes to use chickens and peanut butter sandwiches as examples of things that are serverless. But the point is it still runs on servers. So this is a set of numbers that Jeff Dean, and I think some of these came from Peter Norvig too. These are numbers, you don't have to read it. These are numbers though that every engineer should know. I don't know most of them. You can find on GitHub, there's a more visual kind of version of this too, but the idea is like you should know what the difference between like an L1 cache miss is and a branch miss prediction and a main memory reference. I want to kind of call out 2 of these in particular, which is main memory reference. That's about 100 nanoseconds. A round trip RPC within a single data setter is about 500,000 nanoseconds. So 500 microseconds, it's still pretty fast. It's half a millisecond. So from a kind of user interaction point of view, it's pretty slow. But these things are pretty different. So I think the thing when people talk about service or like functions as a service, maybe a little bit more descriptive version of what it is. These are great when they're stateless, but like stateless is sort of a semantic thing, right? Like you can think about what the correctness means and things like that. But from a performance point of view, like caching is still going to matter, right? Like the difference between having something in memory and going to another service, that's a 5,000x difference, right? So there are certainly things like services that you can build using functions that are totally independent of everything else, that don't require any external things. That's sort of like there's trivially parallelizable MapReduces that you can also write. Yeah, great. Those things exist, but that's not the common case. And I think the kind of word of warning here, or lesson I think a little bit that I want people to take away is like, functions as a service is a great thing, but it's not like I've heard like, oh, we're going to skip over microservices and go right to functions. It's like, those are just different things and they have totally different applications. And there are like some uses for functions, like if you want to like run a hook whenever a file gets written to S3 or something like that, great. But there's a lot of cases where having a little bit of context, maybe in the form of a cache, can be really valuable. Cool. Great. So lesson 3, we talked about independence and like why you should adopt microservices. What do I mean by independence? I think this is something that Google kind of got right. I don't know if it was by accident or not, and maybe it was just through like force of will of Jeff and Sanjay, or maybe they can just like type faster than everyone else, so they sort of won. But you could imagine that independence sort of means that like every team makes every decision totally separately without talking to anyone else. And you kind of get this sort of anarchy in a way, like go pick your own stack. It'll be great. That's one, you're gonna end up with a lot of redundant work. Like you're gonna build, every one of those teams is gonna build some of the same things over and over. And as an organization as a whole, it's gonna be pretty bad. If you think about things like security, about monitoring, about deployments, like it's gonna be a mess. And I mean, my own kind of bias in this is like monitoring, like even if you manage to get every one of those teams running their own languages and frameworks and who knows what else, to actually like emit metrics with the same names, which would be amazing if you even did that. That those metrics are even going to mean the same thing is really going to be hard. Like you're going to be comparing apples and oranges all the time. So really, I think what people should be aiming for is something a little bit like this. Like every ant gets to choose their own path and they could cut their own part of the leaf. But in the end, there's just like the forager ants and like the farmer ants, right? Or whatever the other kind is. So you have a few specializations, but it's not as though everyone is making their own choice. At Lightstep, we talk a lot about hipster organizations and kind of compare that with traditional enterprise in a way. And I think there's a idea that like that hipster companies are adopting microservices faster, but I think they make this mistake a lot in that they don't have the kind of organizational structure, rigor, communication, whatever it is that helps them actually like pick the right set of processes, to pick the right frameworks. I don't like care what the framework is, but I think you have to pick a small number. And I think this is a thing, Google in the end, like there were 3 and then 4 languages that you could use. And those were like the production approved languages. And, you know, we knew that each of those things, you know, it supported the authentication system. It supported Dapper. Like those things were, as an infrastructure implementers, it made it possible to like actually provide service to the whole company in a way. Cool. I'm going to keep flying through. So lesson 4, beware giant dashboards. So we found a regression. Something bad happened. Everyone can see it, right? So the idea of sort of observability, I think as a word, goes back to Twitter when they were trying to figure out like not only to like there's a lot of whales failing. And they were trying to not just like monitor their system, but actually understand it in a way, right? To observe what's happening. And I think there's an idea that like, okay, of course, the first thing you need to do is gather a bunch of data, but that's just like the first thing. Like you also need to be able to understand that in a way, right? So like the culprit is not evident from what's going on here at all, right? We don't understand what the root cause was. And I think that observability sort of boils down to like 2 things, right? So the first thing is, so we have to measure things. We have to detect the signals that are going to tell us when something is going wrong. Hopefully this is something that matters to your users. Something like end user latency, something like error rates, but something that you can identify as like important to your business in some way. And the second thing you need to do is you need to refine that search space. And I choose refine specifically, not something like visualize, because while your visual cortex is an amazing piece of machinery, like the state space is just like too big for humans to understand. So it's really important to be able to refine that in some way so that you can try to understand the variation in those signals. There's a talk that was given internally at Google by Cody Smith, who ran a bunch of web search SRE, which unfortunately is not public, but he talked about how they built SearchMon, which is sort of the infrastructure around web search for monitoring. And in the end, it was like this wonderfully simple thing. I think there were 12 graphs to like understand all of what was happening in web search. And like those 12 graphs, you know, along with like 1 second resolution and the right kind of framing. It like let them understand very quickly what was going wrong and identify the problems and act extremely quickly. And you can kind of imagine that there's like this like huge state space, which I'm trying to represent in this way that apparently looks a lot like Minesweeper. It's not Minesweeper, but there's this huge kind of state space that your application can be in. And say you just had a problem, you rolled something back, and you want to know like, is it fixed yet or not? Is it something that like you've gotten back into a good state or not? And you're not going to do that by sort of like trying to understand what the state of every service, what the state of every interaction is, what every host is. What you really want to do is like reduce, right? You want to project out of that space in some way. And if we can sort of project into a couple of meaningful dimensions, then we can kind of understand, is this a good state that we're in? Of course, it's not really two-dimensional. There's lots of other dimensions in lots of other ways. Yeah, I think the idea is like we need to be able to reduce that and like have tools that'll help us do that. I don't think we're going to get to the point where like tools are just automatically like rolling back the right thing, the right service, or fixing our bugs for us. But the tools really need to help us as humans like lower the kind of dimensionality of the data to a point where we can kind of comprehend it. Cool. Lastly, a little bit more closer to home. So just a quick kind of refresher for folks about what I mean by distributed tracing. So you've taken your sort of square-shaped monolith and broken it into a bunch of still rectilinear pieces. And what's really important in understanding when something goes wrong is how a particular request passes through that system, right? How do you tell the story of that request as it passes through? But let's talk for a minute sort of for real about data volume for a second. So, this applies to tracing a little bit to logging as well. So as you sort of increase the size of your system along various dimensions, like how does that impact the amount of trace data that you're going to collect? And I guess by extension, how much is it going to cost you to collect that data? So transaction rate obviously is going to be a factor, but that's kind of okay because as you do more transactions, presumably you're doing more business, you're making more money. So like paying a little bit more for infrastructure is totally fine. But you're also going to have to think about the number of microservices. So now it's like, oh, you've decided to split something for, I don't know, ship your org chart sorts of regions or whatever, and now you just increased your overall spend on your observability tools. That's not so great. And maybe you think you can get away with like not independently logging in each of those tools, but both there's like independent things that are happening in these different services that are important, and there's a lot more glue between them, right? When you had one function calling another function in the same process, like not much was really going to go wrong between the two of those things. So it didn't really like measuring them independently, like one stopped and the next started. That was sort of the end of it. Now you have like RPC boundaries, you got networks, you got hosts failing, all kinds of things can happen in the middle. So understanding like when one process sort of like begins a request and when it's received is now a really big deal. Of course, you're gonna have to pay for all this stuff in terms of network and storage, and you're gonna wanna keep it because you wanna know what's not only happening right now, but you wanna know what's happening last week or the week before or whenever you wanna compare your service to. So all of this adds up to be, as it turns out, a lot. And so I think looking back at what was done at Google, again, sort of taking, Dapper was built, again, largely for things like web search and ads. And it turns out you can, like tracing and other instrumentation can impact a service in a couple of different ways. One, through sort of the latency itself, like you can put more computation on the critical path. It turns out that was basically never a problem for Dapper. So Dapper continues, as I understand it anyway, like every request that runs through web search hits the Dapper code path. What the other impact is on latency effectively, or excuse me, on throughput effectively through, things that you have to do sort of offline. And one of the big things you need to do is store this stuff. So the approach that Dapper took was basically, it had to do this in a kind of coordinated way, but we would hit the instrumentation point and then we'd flip a coin. And 99.9% of the time, we would just throw the data out, like forget about it, doesn't matter. And if you're doing 2 billion requests a second and you're throwing out 99.9% of the data, it turns out you still have a lot. It also turns out that web search is kind of boring from an API point of view because it's like text in, search results out, and most of that text is the string GMAIL or FACEBOOK. And that most people are just actually doing DNS requests through Google anyway. Anyway, all of this stuff, it has to get buffered, it gets pushed out of the process. There's some sort of like regional storage that kind of gets passed along. And then eventually we're going to do some sort of global aggregation so we can run a MapReduce over this or something. And we actually do another 10x reduction in the amount of data. Again, there's tons of data. We're just looking to do sort of like an aggregate latency analysis, so this is totally fine. But kind of back to the first lesson in a way, like this made sense for for web search probably doesn't make sense for everyone else. I worked on a service at some point at Google where we were doing, I'm going to, talk it up. I think we were doing 100 requests a second, and like, just keep all of them. Like, they're all probably valuable, and it doesn't cost anything to keep 100 requests per second. So just as a kind of like maybe proof point in a sense that you don't have to make that choice. So at Lightstep, we take a pretty different approach, which is that we actually keep all that data all the way through sort of regional aggregation. And then, of course, we do some sort of filtering and further aggregation, but we do that in a much more nuanced way, and we can do that sort of on demand. So in the end, actually, for our bigger customers at Lightstep, I actually think we keep a smaller percentage overall, but each of those pieces of data that we keep are much more valuable than just a totally unbiased sample of things. So yeah, again, think about the scale that you're operating at, and yeah. Okay, almost done, just a few more things to say. So I think what I tried to kind of highlight is two big drivers for microservices. Like we talk about like horizontal scalability and things like that. Like you can do that in lots of ways. I think the really important thing about thinking of independent services with independent SLAs and their own sort of like charters in a sense, that's about team independence, and that's about scaling your engineering organization. And I think a theme in all of this is like understand the scale that you're at. Like there's a big difference between 2 billion requests a second and everything that's less than 2 billion. Think about what you mean by independence, like think about ants. And then, in terms of observability itself, like really, I think the goal here as an operator in this should be think about like what are the things that you need to know to help answer your own questions, right? You're going to go into an incident with a bunch of state, a bunch of questions that you want to ask. How do we make sure that the answers are sort of at your fingertips for that? That's pretty much all I wanted to say. Feel free to like tweet me later. I'm happy to take some questions. Yeah, I don't know. What do people think?